Hello and welcome back. This is part 2 of Notes 1F, where we've been finding homes for puppies. So you were given 5 more to work on, 4 that I hoped would be fairly easy, and then 1 that would be a bit of a challenge. So let's first go over those. So the first one was aluminum. So aluminum symbol is Al, and atomic number is 13. So we have 13 puppies that we've got to find homes for. So it's got 13 electrons. So we're going to put those 13 electrons into our basket. We're going to go out into the neighborhood. We're going to go to First Street. We're going to go to the Smiths, and they're going to take 2. So we still have 11 puppies in our basket, so we've got to keep going. There's no more houses on First Street, so we've got to go to Second Street. There's a Smiths on Second Street, and they will take 2 puppies. There's also a Peterson's on Second Street, and they will take 6. 6 plus 2 plus 2, that's 10. So we still have 3 left in the basket, so we've got to keep going. We're going to go to Third Street, the Smiths, and they will take 2 puppies. And that means we have 1 left. So we've got to keep going. Now the next house is the Petersons. They'll take 6 puppies, but we don't have 6 puppies to give them. We only have 1 puppy to give them. So that 1 puppy is all we're going to give them. So that would be the electron configuration for aluminum. If we want to figure out the number of valence electrons, we're going to bracket in that last street and add it up. 2 plus 1 is 3. 3 valence electrons in aluminum. All right, the next one you were supposed to do on your own was magnesium. So magnesium is number 12. So it has 12 electrons. So there's 12 puppies that we need to find homes for. So we're going to put our 12 puppies in the box and put our 12 puppies in the basket and carry them out into the neighborhood. So we've got 1 First Street and the Smiths, and they will take 2. We still have 10. Got to keep going. Second Street, Smiths take 2. Petersons take 6. That's 10. So we've still got 2 left. We got to go to Third Street to the Smiths, and they take 2. And then that's it. We don't have any left in the basket. So that is our valence electron. So magnesium has 2 valence electrons. The next one I asked you to do on your own was silicon. Silicon is number 14. So it has 14 electrons, 14 puppies we need to find homes for. We're going to go out into the neighborhood onto First Street. No, Smiths will take 2. Second Street, Smiths will take 2. The Petersons will take 6. And that's a total of 10. So we've still got 4 left. So we've got to go to Third Street to the Smiths. They take 2, but we still have 2 left. So we've got to go to the Petersons. They want 6. We don't have 6 to give them. We only have 2 to give them. So that's going to be 2. And then we bracket in that last street and add them up. 2 plus 2 is 4. 4 valence electrons. And then chlorine was one that I thought maybe you'd be able to do. That's got 17 electrons because its atomic number is 7. So we're going to put those 17 puppies in our basket, go out into the neighborhood, and try to find homes for them. First Street, the Smiths take 2. Second Street, the Smiths take 2, and the Petersons take 6. That's 10. So we have 7 left. So we've got to keep going. Third Street, Smiths take 2. So that means we have 5 left. So next we go to the Petersons. Now the Petersons can take 6, but we only have 5 to give them. So that's going to be 5. Bracket it in, 5, 6, 7, 7 valence electrons. Now last, I told you that this one was going to be a challenge because you would need to use the diagonal rule to get it correct. And that one was copper. I challenged you to do the electron configuration for copper. Now, copper, Cu, is number 29. So we have 29 puppies we need to find homes for, 29 electrons. Same rule applies when we first get started. We're going to go to First Street and the Smiths, and Second Street and the Smiths and the Petersons, and Third Street and the Smiths and the Petersons. But that only gets us to 18. 6, 7, 8, 9, 10, and then 6 plus 2 is 8, so that's 18. So we had 29 minus 18. We still have 11 puppies that we've got to find homes for. So we've got to keep going. But we have to use the diagonal rule. And for that one, I don't want to scroll up and mess up what I've written. But for that one, you've got to remember that it doesn't it doesn't go straight from left to right. That should be enough. That should definitely be enough. So we got to remember that our diagonal rule comes in like this. So far we've done that. Like we're there. We've done 1s2, 2s2, 2p6, 3s2, 3p6. So following our diagonal rule, what comes next? 4s2. So that's what we need to do next here. 4s2. So we had 11. We're now down to 9 left. So we've got to keep going. So the diagonal rule ends here. So it comes back up to the top again. So 3d10 is the next one we're in. We only have 9. So that's where we would stop. 3d9 because we didn't have 10 to put in there. And if you add that up, it should be 29. Now, here's the thing. The outermost energy level is this one here, because that's energy level 4. Yes, the electrons did fall into the 3D energy level after they fell into the 4 sublevel, but the 4 level is still the outermost level. So that 4s2, that's your outermost street. That's the last street you went to. It's that diagonal rule that messes us up. That's why I said this one was a challenge. So how many valence electrons are there? Well, only 2, because we've only got 2 on that outer energy level. Okay, so that's that. Okay, now that was a complicated way to, I won't scroll, there we go. That was a complicated way to figure something out, okay? Like, I want you to know how to do that, but at the same time, you don't have to do all that to figure out the number of valence electrons in any given atom. The periodic table is organized in such a way. Remember, we talked about the fact that the valence electrons is one of the patterns. And one of those patterns is that each one of these families have the same number of valence electrons. So the periodic table, the group number, except for the transition metals, all right? So that I've told you before that the transition metals, they don't play right. They don't play fair. They don't follow all the rules. So for now, we're going to ignore the transition metals because they aren't quite, normal. So you don't have to understand those until you get to chemistry. So the transition metals aside, the family number can tell us the number of valence electrons. Everything in family 1 has 1 valence electron. Everything in family 2 has 2 valence electrons. Now, we're going to skip the transition metals because they don't abide by the rules, but check this out. There are 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When we get up here to family 13, guess what number we subtract? 10. So 13 minus 10 is 3. So everything in family 13 has 3 valence electrons. Everything in family 14 has 4, 15 has 5, 16 has 6, 17 has 7, 18 has 8. So we've got 1, 2, skip a few, 3, 4, 5, 6, 7, 8. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So everything in this row, or not row, column, everything in this column has 1 valence electron. Everything in this one, 2, 3, 4, 5, up to 8. Okay? Now, that's what this lovely thing here is really telling us. These little dots are the Lewis dot diagrams, and the Lewis dot diagrams tell you the number of valence electrons that are in an atom. So you can very easily look up here and see. So I want you to tell me, how many valence electrons do each of those elements have? Pause, figure it out, come back, get the answers. All right, you've unpaused, you've got your answers, now you want to check. All right, hydrogen has 1 valence electron. Carbon has 4. Argon, 8. Lead, not PO, polonium, not phosphorus by itself, but PB has 4. Calcium over here, 2. Oxygen right there, 6. And aluminum, 3. Did you get those right? All right, so using those dots, those Lewis dot diagrams, you can tell the number of valence electrons that an atom has. And they're used a lot by chemists because it's an easy way to tell how two atoms are going to interact chemically. Because when atoms are interacting chemically, it's due to their outer electrons. It's due to their valence electrons. So sodium. So sodium, Na, it's in family 1. That means it has 1 valence electron. So easy. 1. Done. Okay. Carbon is in family 14. So it has 4 valence electrons. Now, what's interesting about valence electrons is they really do kind of spread themselves out evenly around the atom. So carbon bonds with so many things. We are carbon-based organisms. All living things on Earth that we know of, for the most part, are carbon-based. It's because it's what's called organic, because it means it's got carbon and hydrogen bonds. Carbon makes these things called rings and rods, these chains of carbons that are just carbon. So it bonds with itself really well. It bonds with lots of other things. Why? Because it's got 4 places that are empty. It's got an empty spot up top next to the one it's got an empty spot. So it's like got all these hands reaching out going, hey, grab my hand, hold hands with me, make a new compound. So that's why there's so many compounds that have carbon in them as their base, because carbon's out there going, hey, let's bond, let's make something new and exciting. All right. So carbon looks like that because that's why it behaves the way it does, because it looks like that. All right. Oxygen has 6 valence electrons. So that means that 2 of the spots are full, that it's got, well, I want that right. It's got 2 here and 2 here and can't take any more and it's full. But then it's also got 2 sides where it's willing to grab onto something. So that's where it grabs onto 2 hydrogens, for example. Now, argon has 8 valence electrons. It's a noble gas and it's stable. So this explains why it's stable. All right. It is stable because it has full valence electron. It's like a full balloon bumping into something. It's not going to do anything because it's got that complete outer energy level. So that means that we've got 2 here, 2 here, 2 here, and 2 here. So everybody's happy, full, stable, 8 valence electrons. Aluminum in family 13, 3 valence electrons. So they're going to distribute themselves around the atom. Chlorine, family 17, it's a halogen, so it's highly reactive. And halogens are only wanting 1 valence electron. So they've got this 1 empty spot. And that's why I call them Mr. Steal Your Girl, because they will go out and they will take the one that they need. So that means he's only missing 1. So if he's only missing 1, that means he's got 2 and 2 and 2, and then just 1 empty spot right there. All right, and then potassium, K, is back into family 1 again. So back to just 1. All right, I know that even when I've got students in class that can tend to struggle with this review part down at the bottom of the notes, but I tend to be there to help you with it. So do me a favor, read over the question, pause the video, read over the questions, answer as much of them that you can, take a whack at it, take a guess, see if you can do it, and then unpause it, and I will give you the answers. All right, you're back. So valence electrons are the ones in the outermost energy level of the atom, and they are responsible for determining if the atom is stable, reactive, or somewhere in between. Electron configurations use energy levels and sublevels. I want the sublevels and how many electrons they can hold. So we have sublevels. These are the homes. These are the names, the Smiths and the Petersons and the Daniels and the Franklins. And the Smiths will hold 2, Petersons 6, Daniels 10, Franklin's 14. Then how many total electrons will each of these energy levels hold? So first energy level only held 2 because it only had the S sublevel. The second one holds 8 because it has S and P. The third one is 18 because it has S, P, and D. The fourth one is 32 because it has all 4. Fifth is 32 because it has all 4. Sixth is 32 because it has all four. And seventh is 32 because it has all four. And if you add all that up, you'll get 118 because that's the total number of electrons possible since oganesson is number 118. All right. After this, I need you to work on big question number 5, which is posted as the next thing in Schoology. Have a lovely day. Make good decisions. Bye.